Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm sorry?
Oh, do you really
It's okay. Oh, it's okay.
Just don't. Yeah, why don't you go and sit
Yeah.
You can like slide one chair and then. Good. Well, before we get a fire marshal in here. Okay, so we are thrilled to have Madhu sit in here. He's here for about a month. I guess this is about the middle of your visit?
Pretty much.
Yeah, so we're really happy to have him here. If you want to talk to him, he's still here for another couple of weeks. And this is somewhat of a survey talk, right?
Yeah.
So I don't know much about error correcting codes. So he will tell us about error correcting codes, progress, and challenges.
Okay, so this is a talk that comes out of it's a proposal that I wrote, so very little of my intellect going into this.
I see. Is that like a hint that you want some money or something? Okay.
So mostly it's actually going to be a very lightweight talk. I don't think there'll be any theorems that will be proven. If anything, it's just a collection of very old open problems which will be listed in new font, so we can recognize them. There's been a lot of work going on in error correcting codes, and some of the goals are to sort of summarize the various different directions all in one talk, so we can sort of compare this stream of work against that, as opposed to sort of marching down any one of those streams. So, okay, the problem is an ancient one that starts all of this. There's a sender who wants to send some messages to the receiver. There's a noisy channel, so the sender wants to say we are not ready. The noisy channel flips something and says we are now ready. So we don't want errors like this in the digital world. So if the information is digital, reliability is very crucial, and the area of error correcting codes tries to study this issue. There were two seminal works in the late 1940s, Shannon and Hamming. I'll start by describing Shannon's model and then go on to Hamming's model and tell you a little bit about what both of them said. So in Shannon's model, the crucial element of the modeling is how do you model the noise? And he said, well, let's assume that the noise is probabilistic. He also introduced two very important elements, the encoding element and the decoding. He said rather than having the sender send the information directly to the channel, he should do something to it before he does it, and the receiver should do something with the received information before trying to interpret it as the information that was being sent. So the sender, what does the sender do? It encodes, which takes a stream of k symbols over some alphabet sigma. Sigma could be the binary alphabet or could be some other finite alphabet. For our purposes, it's finite, though Shannon actually allowed all sorts of other things. And expands it to something longer. So encoding over here refers to some sort of an expansion operation. Decoding, on the other hand, takes the long stream in sigma to the n and compresses it back to a k-letter string. And for this talk, we'll just stick to a relatively simple probabilistic model, though actually many others were considered in Shannon's original paper. So the probabilistic noise model that I'll try to describe the results in is that every letter in the alphabet that's being transmitted over here is reproduced here faithfully with probability 1 minus p. On the other hand, with some tiny probability p, you output a random letter of the alphabet other than the one that you saw. So and the focus is to design good encoding algorithm over here and a good decoding algorithm over here. And all of this, by the way, Shannon's work is 1948. Computers didn't quite exist then, but he nevertheless made them part of his architecture in the sense of saying, well, we want good encoding and decoding algorithms. So this was the model under which Shannon considered the reliable communication problem. I won't get to the results yet. I'll start describing the results much later, but now I want to switch to the other model, which was Hamming. And Hamming differed from Shannon in one fundamental way, though there were many other sort of technical ways in which they differed. I think one of the main aspects that Hamming focused on was that the error is not going to be random or probabilistic, but subject to an absolute limit on the number of errors that can happen. So maybe out of n symbols that you're transmitting, t of them may be flipped. How and which these symbols would be was absolutely adversarial. There was no control that you had. And in particular, the order of quantifiers was all different. It was not as if you defined the model and then said, let's try to design a coding algorithm for it. But rather, you designed a coding algorithm, and then the adversary comes along and says, now let's see how to make errors in this setup. And Hamming also stylistically changed the focus of the work. So rather than focusing on this encoding function, which says, how do I expand the strings, he just said, let me just look at the kind of strings that I get when I expand them. Okay, so k is smaller than n. Sigma to the k, the encoding maps it to strings sigma to the n. Not every string is being mapped to. What kind of a set do I get over here that allows me to correct any pattern of up to t errors? So this was the fundamental question that Hamming raised, and in a sense, for a long while, these two languages were, kept very, very separate. People do not like it if I define an error-correcting code. Even today, by the way, Venkat and I wrote a paper, and we got lots of complaints saying we are referring to this as the error-correcting code, but it's really that. So it's not reasonable to say encoding is the same as the code. Okay. All right. So there was a lot of differences over here. So broadly in coding theory, the kinds of problems that we tend to see are based on these two issues. First, there's combinatorics. Never mind the complexity of the encoding and decoding algorithm. What can you do? Design the best possible error-correcting codes. So in particular in the Hamming model, this is a very, very important and challenging question. And then there are questions based on which are sort of come into the mix of probability and algorithms. It says design good encoding algorithm and decoding algorithms. These algorithms may try to correct either random errors or worst case errors and try to do the best you can in all of these cases. And so in this three-part talk, I'm going to first focus on the combinatorics, tell you what the state of the art is, and some very important, interesting questions. There'll be very little, I'm warning you, there's very, very little technically that's that I'll say in this talk, but if you want further pointers and so on and so forth, feel free to look at my homepage where I have some notes on coding theory where you can fill in all the, you can see some of the proofs of the claims that are made here and see why other proofs are not included. Okay, so this first part, I want to talk about combinatorial results. In the other two parts, I'll be talking about algorithmic results in the two different models, the random error model and the worst case error model. So let's start by a few definitions. Hamming started by defining this notion of what he called a distance between strings. Okay, so as such, we are looking at a collection of sequences of length n, sigma to the n. We start by looking at what's called the distance between two strings x and y in sigma to the n, which is the number of coordinates I where xi is different from yi. So x is an n-bit string, n-letter string, y is an n-letter string. The number of coordinates where they differ is what we call the distance between them. And Hamming noticed that the distance of a code is what's really important about an error-correcting code. This is the parameter that you want to optimize. And the distance of the code is defined to be the minimum over all pairs of code words, strings x and y that you can obtain as the image of the encoding function. Over all such pairs, you want to look at the distance between them, and you'll consider the minimum that you can get over distinct pairs. PowerPoint gave me a lot of trouble trying to generate the inequality sign, so I just didn't say that. But x and y are distinct. Otherwise, that distance would be 0. And what Hamming noticed was that, well, if you want to design a code which corrects t errors, you should make sure that there are no two strings x and y which are at distance 2t. Because if two strings are at distance 2t, you pick the midpoint between the two, then that will be a distance t from both of them, and then you cannot figure out which one it came from. So code of distance 2t plus 1 corrects t errors. So what are the main questions in this theory, the Hamming theory? There are 4 parameters of interest really. There's the length of the code word, n, the length of the message, k, the distance, d, of the code, and the alphabet size on which you're working. And these 4 parameters sort of tell you what the terrain looks like. How well can they play against each other? And what we would really like to do is to sort of make sure you're encoding as many symbols in the message as possible, using as short a code as possible, while you maintain the distance as large as possible. And clearly you can't just let them all be free. In particular, n is an upper bound on k and d. In fact, it also turns out to be an upper bound on k plus d, and so on and so forth. So you have various constraints among them, and those are what you want to study. Something that's not so obvious by looking at it is what do you want to do with this size of the alphabet? In a sense, it's not under your control what the size of the alphabet is. It's whatever the physical channel gives you. It says you should put in bits, you get out bits. Well, then sigma should be, q should be equal to 2. But in a sense, mathematically, it turns out that it's good to play with this alphabet size also, even though the channel may not give it to you. And if so, what you would like is to get codes of a given choice of n, k, and d with as small an alphabet size as possible. In a sense, that's what is the right parameter. That's the right direction in which the optimization should go. So since there are too many parameters, we'll try to reduce them by at least 1. And you can reduce them by at least 1 by saying, let's just study the ratio of k to n. Let's study the ratio of d to n. So the ratio of k to n is called the rate of the code r. Delta, I will keep calling it distance, but depending on what I got in my head, I mean either the ratio or the actual number. Delta will be d over n. And we really would like to study how do r, delta, and q relate with each other. Okay. This is the fundamental question in coding theory. I'm going to give you very simple results once again. So anything that I'm going to prove will be too simple for words, but that's the way this talk is. Okay. So here are a few simple results. I want to relate r, delta, and q. These are the 3 parameters. Let's see how they relate with each other. So in order to study this, we'll introduce some simple notions. Let's denote by ball of radius r around x the set of all points y whose distance to x is at most r. Okay. So, yeah.
R is not the ratio.
Oh, this is little r. I'm sorry. Capital R, little r. Oh, yeah, oops. I'm sorry. Okay. No. I'm not going to change it. Sorry. So yeah, sorry. This is little r, but we won't use it more than. Okay. So one more line which will involve r, and after that, hopefully, we'll never mention this radius r again. Or at least use that notation. So the volume of this ball is what's really important to us. And this volume is a function of what's the alphabet size that you're working with, how long are the words, and of course the radius of the ball. So volume in an alphabet of size q, of words of length n, of radius r is the size of this ball. How many points are there in this ball? This ball is a very fundamental quantity, and it leads to another very fundamental quantity, which is the entropy function. I don't know how many people have actually, just give me a quick show of hands, have never seen the entropy function? Anyone here who hasn't seen the entropy function before? Wow.
How many people have seen it?
Because otherwise,
Oh, okay. How many people have seen the entropy function before? Oh, Avi, okay, for this, okay. All right, this is a function that we're going to sort of keep talking about throughout the talk, okay? So it's useful to at least study its definition. And the way I'll define it is the entropy function of delta relative to q is the constant, some constant less than 1, is the constant such that when you take the volume of the ball of radius delta times n in sigma to the n, where the size of sigma is q, then that number is roughly q to the c times n. So the volume of a ball of radius n delta n is going to be q to the h sub q of delta times n. So this is, I'm more or less taking this as the definition of the entropy function. It's there are many other ways of looking at it, but from the combinatorial perspective, this is what you would come up with. So the important thing is to realize that this is actually, it's a well-defined notion. So in particular, h sub q does not depend on n. It's a constant which is not a function of n, but as n tends to infinity, this is the right formula, this works. There is a single constant for which this always works. If you take that to be the definition, this is a very nice thing. Let me just, for those of you who haven't seen it, or like Avi have seen it but too lazy to raise their hands, let me at least plot what h sub 2 of delta looks like. There's delta. There's h sub 2 of delta. It reaches a peak of 1 at the midpoint, a half, and in between it's a sort of a, I don't know, concave, convex, one of those functions, okay? So it looks like that. So what's important about this thing? Well, so we can derive a couple of bounds on the rate of a code relative to the entropy function fairly easily.
For Q equals to, you get actually classical but for other Q it's a little, I mean, if it's been since before, it's a little confusing.
Okay, so well, other Q you can ignore because we'll never talk about the other Q. All right, so good. We will talk about it, but it's just a good way for me to suppress Q out of a lot of notation. Okay, so all right, let's start with the Hamming bound. It's a bound which says that any code should not have too many code words. So it's an upper bound on the rate of a code. And all it says is the following. Well, if you take an error correcting code and around each code word you draw a ball of radius about d over 2. Well, these are disjoint, right? Or, if you make it strictly less than d over 2, these are disjoint. And so that gives you an upper bound on the number of code words. Roughly, if this is what your space sigma to the n is, this green space, and these red dots over here are your code words, and these are your balls of radius d over 2 around the code words. They're all disjoint. What that implies is, I'm sorry if somebody can't see this, but if the number of code words is q to the k, sigma to the k is the image, so q to the k code words, and the volume of these balls, each one of these balls has volume q to the h sub q of delta over 2 times n. That just follows from our definition of h sub q of delta. And the sum of those two, or the product of those two, better be less than the net volume of the whole space, which is q to the n, sigma to the n. So if you look at these two quantities in the exponent, it says k divided by n better be less than 1 minus h sub q of delta over 2. Okay? So it gives you an upper bound. It says that the ratio, there cannot be too many code words. I mean, that should be obvious. I'll state this thing numerically in a couple of slides, but this should make pretty clear sense. Any questions? Jennifer, no? Yes? No questions about this. All right, so fairly simple bound. There's a construction, there's an existence results for codes which is called the Gilbert-Wassermann bound. It's also called the greedy bound. Other people who prefer the probabilistic method applied in this case can also derive a pretty similar result qualitatively, though not precisely quantitatively, by just applying, constructing a code at random. So if you just pick a code which has q to the k messages and q to the n things, let's just pick a code to be maximal, meaning you cannot add any single word, any single point in this ball without violating the constraint that the distance between every pair of code words is at least d. Okay? Pick any maximal thing. Well, then the balls of radius d minus 1 around the code words should cover sigma to the n. So the picture is like this. You're starting off, you have an empty palette, and you've added a bunch of code words, and things look like this. And at this stage, you want to say, can I add another point whose distance is d from all the other chosen points? But unfortunately, when you draw balls of radius d minus 1 around the code words, you find there's no green area left. Well, at this stage, you can't pick any more code words. If a code is going to be maximal, it's got to look like this. The balls of radius d minus 1 around it have to cover the whole space. That gives you another bound. This is a thing says the codes can have lots of code words. Q to the k is the number of points that you've chosen so far, times q to the volume of these balls better be greater than or equal to q to the n. Not in the exponent. Who could have ever done that? All right, so, okay, Avi is alert. I didn't realize that. Okay, so this time I'll actually scale this quantity for you. Actually, lots of things are not right about this thing. That should be an h sub q of delta times n. The n should be outside, not inside. And once we do put it in the right form with the q in the bottom, and you do the right scaling, you find that the rate that you're getting, k over n, better be at least 1 minus h sub q of delta, okay? And for a maximal code. So this gives us two basic bounds on how well the code can perform. And by the way, I mean, just in case you think we've found sort of the formula for the rate, you know, notice that these two quantities are different. Okay, over here you have the entropy with respect to delta, while over here you have the entropy with respect to delta over 2. And in the entropy, so with respect to delta, we might say, well, you can get a code of rate about that much if you want delta to be that, while the bound rules out codes of rate that much. Okay, so there is a wide difference between those two quantities. So which is right? And the unfortunate story is, well, there's 50 years of research since Hamming introduced this problem, but this problem remains essentially, you know, open. We know a few answers, but we don't quite know what is the right answer. In particular, we don't know that the Hamming bound, which is so cheap and obviously wrong, is wrong. Okay, so it may well be that the Hamming bound is right for certain choices of delta. The Hamming lower bound. The upper bound. For q equals 2, oh sorry, the this one over here. It's not, okay, so we'll discuss this in a minute, and we'll see which way I mean this. So let me start by focusing, giving you a little bit more of an update on the state of the art. No more proofs, just statements. What happens in the binary case? Binary case, q is 2, the alphabet that we probably care about most in this setting. And let's consider two very special cases. So by the way, I mean, typical talk on coding theory would plot all of these graphs and tell you, you know, look, we found a bound which looks like this, but there's another bound which looks like that, and there's a third one that's going like that. And I'm going to try to do this talk without graphs as far as I can. Well, modulo whatever I drew there, the rest of the talk is without graphs. I want to say that there's still results that you can sort of separate out which are asymptotically interesting and still you know, and in many cases wide open, even though in some senses we've sort of figured out that that point is about right and that point is about right, etc. So what are some interesting ways of studying the problem? So one thing we can try to do is study the behavior of our codes as the rate tends to 1/2 in a binary code. Okay, this is about what you would expect is the best. As the distance gets close to 1/2, you would expect that in a binary code you can't get too many code words. Yes? Right.
Sorry for that correction. Now, so far, these bounds apply for nonlinear codes.
Yes, yes. Right, right.
Do they still apply if you expect the code to be linear?
True. Very good. So firstly, you should not be sorry for interrupting, because I do want people to interrupt. Nati asked me to ask everybody to interrupt. And secondly, yes, you're right. So I have not been talking about the distinction between a very nice family of codes, the linear codes, and the nonlinear ones. In general, when you can get good codes, you would like them to be linear. You know, get some parameters, you would like them to be linear, and all the things that I've said so far, well, not many of them, can be achieved with linear things also. So in particular, Gilbert showed that when you pick these codes at random, greedily, then you get the bounds that I quoted, and then Vashamov proved the same thing for linear codes. And there's even a slight difference between the two results when you look at them under a microscope. But Vashamov is better. So far as we know, when we construct codes, we would like them to be linear, but when we try to rule them out, we'd like to rule them out in the more general setting. Okay. So in this case, now we're going to look at the distance of the code to be roughly 1/2 minus epsilon. So every pair of code words is differing in 50% of the bits. Now these are bits, you don't expect them to differ in much more than 50%, but as you get close to 50%, how can you do? And there are results in the literature which pin this number down pretty effectively. On the one hand, the rate of the code should grow as omega of epsilon squared. And this is what you would get if you picked a random code or a random linear code, or if you sort of did the careful analysis of the Gilbert-Wassermann bound that I just described. This is the number that you get. Okay, this is roughly related to the tail inequalities, which says that if you expect a random variable to be 1/2 the time, the probability that it's 1 with probability less than 1/2 minus epsilon is less than 2 to the minus epsilon squared times n. So that's the epsilon squared that we see here. On the other hand, there's this famous, very intricate linear programming bound, which says that the rate is roughly O tilde of epsilon squared. Okay? So this is Michaelis, Rudimich, Ramsey, and Welch. It's a famous bound. It's also called the JPL bound, named after the Jet Propulsion Laboratory where they did the work. This is a very hard result to prove. I know Nati has worked on it. Maybe also you, Latsi. I don't know. But this is this is one of the sort of very hard pieces of work in this literature, and it takes quite a bit of effort to prove. And this is one of those results. In fact, I would say, compared to the ease with which I can prove the lower bound, give me any result which shows that roughly epsilon squared is the best rate you can achieve, and give it to me with an elementary proof. I don't know of a good elementary proof. I mean, this uses the theory of orthogonal polynomials and so on. So this is quite sophisticated. This would be maybe the first open question that we encounter here. Okay, I didn't list it, but it should be. There are probably log factors in the epsilons in the upper bound. The lower bound, I'm quite sure is right, because I can prove it. What about the other extreme? So this is the one extreme. The other extreme is when you have very small relative distance. So now we're going to take the distance delta and push it to 0. So we're looking at a code whose distance is going to be very close to 0. You're trying to correct a few errors. How well can you do? And here, Nati, correct me if I'm wrong. Do you think this is... So I think at this state, you can take the best bounds that you have. They don't give you... So as you let delta go to 0, their performance is roughly looking like 1 minus little o of 1. This little o of 1 is as a function of delta going to 0. And Elias doesn't do any better. So all of the bounds are definitely, Elias bound, for example, I think definitely majorizes this for every choice of delta, but how it majorizes it is vanishing. So in a sense, as you're going closer and closer to delta going to 0, this is, by the way, this is the Hamming bound without the 1 minus little o of 1. And some people have managed to add a little o of 1 times h of delta over 2 when delta go, but that function is sort of vanishing relative to the higher order term when delta goes to 0. Okay? So in a sense, over here we have, we haven't achieved better progress. And there may be a good reason why we don't have progress, which is better than that. So I claim this is Hamming, but this is, the little o of 1 is not Hamming, but without the little o of 1 it is. And now the reason this is all sounding kind of fishy and plausible that Hamming might be right is when you look at the case of constant distance. So we are no longer looking at the case where delta is tending to 0. Actually, we are looking at the case where delta is tending to 0, but in a very strong way. The distance d is some fixed constants, 19, and n is now tending to infinity. How can you build a code which has distance 19 while distance is tending to infinity? In that bound also we have some things that we can say. You can look at the difference between n and k. What does it look like? It looks like some multiple of log n. Some multiple, what is that multiple? Is roughly d over 2. The distance that you want divided by 2 times log n to within a 1 minus little o of 1 factor. How do we know this? Well, this side is really the Hamming bound again. I'm just, opening up the entropy function in the Hamming bound over here. And over here is the famous BCH codes, also from the 1960 or something. This I consider a relatively elementary code, but still I think this is a case where I would love to see just a non-algebraic construction which meets this bound, and we don't know of anything. This is a remarkable code. This is the first example that we are seeing of a code which outperforms the random code by a factor of 2 in some, when you measure performance so that it can be a factor of 2. Right, okay. So anything in your thesis is okay. No, eigenvalues are, okay, so I don't want you to use finite field extensions and so on and so forth. I agree that this is somehow this is not a profoundly hard result to prove, so it's kind of hard to say what would you like which would be simpler than that, but there is this question of its scaling with respect to the distance, which is kind of hard and fast over here, and we'd like to know if that could be improved. And also it's scaling with respect to the alphabet size, and that is something that I'll get to in a few minutes. And can you do this with a ternary code? Just get the same result with the logarithm to the right base, and we don't know. Okay, so let me just keep going on with the binary codes. Actually, I'm going quite slow, so but I hope. Yeah, if people are.
Question.
Yes.
It seems like the conjecture right here says for large alphabet size, for large Q, these bounds get tighter.
For large Q, I'll come to the large Q question shortly. Okay. So right now I want to, for one more slide, I'll talk, one or two more slides, I'll talk about the binary case, and then I'll talk about the general q-ary case. Things look very different when you look at large Q, and it's a very nice question. So for general NND, so I want to just recall the original bound. This is the bound, the Gilbert-Varshamov bound. The number of code words can be at least 2 to the n divided by the volume in the space of binary alphabet n sides and d minus 1 sized balls. Okay, this is the result that we've looked at. So we don't know how to improve on this in general. Okay, so can we do better? Can you do even twice as many code words as this number? So if you do twice as much, the asymptotics, the rate r and the delta won't change. They'll look the same. But but still, even when I first taught this result in my coding theory course, one of the students asked me, "So you're telling me that the worst maximal code is the best? Is that the conjecture?" I mean, so when I said the Gilbert-Varshamov bound might be optimal, I said the worst code is the best. So it's possible that you could pick something slightly better. And for a long time, actually, this question remained open, and then it was radically altered by Jiang and Vardy. And this is a radical alteration in the sense they actually put in over here a multiplicative factor which is at least d. Okay, just some complicated function of n and d, but it's at least d. And this is already, okay, so this is not an asymptotic improvement. What you would like to see is 2 to the epsilon times n to see some asymptotic improvement. But to date, we did not even know that you could put, 10 over there as a number. So, very good question. Okay, so it's a very simple idea. So they say, let's look at this graph, which is called the Hamming distance d minus 1 graph. So what are its words? Its words are all the binary vectors, so 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, and so on. These are the words of this graph. And you put an edge between two of these vertices, two of these n-length sequences, n-bit sequences, if the distance between them, Hamming distance, is d minus 1. Okay? So vertices are 0, 1 to the n, the distances. If u and v are adjacent, if the distance between them is at most d, strictly less than d. So what are we looking for when we are looking for a good binary code? We are looking for an independent set in this graph, okay? A large independent set. And the Gilbert-Varshamov bound that we've described is just saying, well, an independent set is at least the number of vertices divided by the degree of this graph. And that's all we've been saying so far. And Jiang and Vardy actually noticed that in this graph, actually the number of triangles is small. And once you notice this fact, there's a very easy or it's easy which direction you want to go in. I think it's a result due to I-type conversion similarity. I just took Avi's word for it. I should have checked. Trust but check. Oh, no. Okay, so there's a result. I forget who it's. It's I-type conversion similarity. Okay, both Nati and Avi agree that this is the right reference. So if a graph has if it has no triangles, then you can actually improve upon this bound, number of vertices divided by the degree, by a factor which is logarithmic in the degree. And if the graph has a small number of triangles, well, you throw away the triangles and then you apply the result. Okay, so it holds also for that case, and so using that, and they just end up concluding their bound. So it's still very elementary combinatorics at this stage. Okay, so modulo this the I-type convolution similarity result, which is some level of sophisticated probability, but it's still something that I can prove in a page or two. I mean, it's not very hard. So this gives us some improvement, but it also gives us hope that there may be many more improvements. We just haven't looked at this quantity carefully enough. So that's roughly the message of this case. So many questions remain open in the binary setting, but here are a few things that are that I would highlight. So firstly, the greedy code, the code that we say we know it exists. Can you give me an explicit construction, an encoding algorithm that runs in polynomial time? We don't have that. And in particular,
so what were they using about the fact that there are only a small number of triangles? I mean, would there be more large independent sets? So
right. So small triangles.
There's no obvious way of trying to.
Well, this is a very locally symmetric graph. Right. It's also the probability that if A is adjacent to B and B is adjacent to C, that A is adjacent to C is also pretty high in this graph. So these are all features that one may be able to use. I don't know how, but there's certainly quite a bit to.
But I mean, were there obvious things that were suggested by this, and it's just that it becomes too hard to get those estimates, or really not?
No, I don't think there are any obvious ideas hanging out there. I think it's just the riddle level.
Very small independent set, and the remaining graph is almost same as the original thing.
I see.
They take some number of vertices and remove it their neighbor, and then the remaining thing is
I see. Okay.
Okay.
Okay, so that's interesting. So I haven't seen the proof, or at least I did see the proof, but I don't recall it as being as phrased in such terms. But yeah, I mean that seems very plausible. So take out small pieces at a time. And okay, so moving on, what would we like with the Gilbert-Varchamov bound? So I don't want to have to draw pictures. So in particular, I think it would be very interesting if we could come up with an explicit construction of codes of distance 1/2 minus epsilon, and whose rate is roughly what's suggested by the thing. The current best constructions that we know have rate about omega of epsilon cubed, and it would be very nice to improve that. And that's sort of one major question that's open over here. Another very important question, I think, is Hamming really tight when delta tends to 0? So of course I may be wrong if Nati's doubts come to light, but I have a feeling that this is actually there's some very decent chances that we may actually be able to find codes which are a lot better than what's suggested by the Gilbert-Varchamov. In particular, we should be able to do something like codes of rate 1 minus c times delta log delta, where c is, so delta log delta is roughly what the entropy function h2 of delta looks like when delta goes to 0. And we may be able to build this with some c less than 1, and that would be very interesting and nice. C equal to half is what the Hamming bound rules out. Okay, and of course the major question of whether you can sort of pin down the rate of binary codes for all choices, not just delta tending to a half,
and delta tending to 0. But that's still open. Of course, that's the question that we are striving towards, but I think these are much simpler versions of the questions, and we still are struggling with those. Okay. All right, so I want to move to now q-ary case. So I think I'll have very little time left for my algorithmic things, but I'll rush over that part. This is going well. So
it's not just a 1 hour talk. I mean, you can definitely.
Okay, we'll see.
Like another
Yeah.
half hour or something.
Okay, sounds good. Okay, thanks. So in the q-ary case, here's a different game we'll play. In fact, some game that you were suggesting earlier. Let's fix the distance that you want to achieve, 10%, whatever, delta, some delta, and then let q tend to infinity. Okay, and what does it mean, q tend to infinity? Well, pick some q which is large enough, and then you fix that, and then you let n tend to infinity. Okay, so you still have n which is going to infinity much faster than anything else, but between the rate and the distance, we want to sort of fix the distance and say how do codes look like. So there's a fairly easy result which shows that the rate of a code better be at most 1 minus delta minus some quantity which goes like order of 1 over q. This order is order sub delta of 1 over q. Okay, so no, I'm sorry. This is no, that's right. It is order of 1 over q. The q order sub q of 1 over q. And this is saying that the rate better not be as large as 1 minus delta, but you also lose a little bit based on the alphabet size. If the alphabet is very small, you lose something. On the other hand, over here, you have a lower bound which says you can actually also achieve this. Your rate is at least 1 minus delta minus a little bit. And how much is that little bit? Well, that little bit is order of 1 over log q. This is what we've seen so far, essentially. I mean, this is the Gilbert-Varshimov bound, the lower bound. So if you just pick the random code, you analyze its numbers, that's what you get. On the upper side, well, we didn't prove it, but there's a result due to Plotkin. It's again, fairly elementary stuff which implies this. And so in between these two things, there's a natural question: what is the growth? So is it 1 minus delta minus 1 over log q, or is it 1 minus delta minus 1 over q? And here's a remarkably surprising result which came along in the 80s. And algebraic geometry ended up giving us codes which had a rate which was at least 1 minus delta minus roughly 1 over square root of q. Okay, so a lot better than the random codes. So by the way, this is a recurring phenomenon in error correcting codes, whereas in most of other extremal combinatorics we are sort of chasing the random object and trying to get our hands on it. Here we are way ahead of that game. So there's a phrase in coding theory which says that every code that almost every code is good except the ones that we know. But really it should be almost every code is good except the ones we know, which are even better. I mean, so it's really the BCH codes are better, the Hamming codes are better, the Adamart code is better, the Reed-Solomon code is better, and algebraic geometry codes are better. They're all better than the random object. Okay, so this is another one of those cases. We're getting a whopping increase over this, but then it only increases our puzzlement. So also, by the way, there's a negative surprise which I didn't get into much over here. BCH codes, which originally yielded a rate which was 1 minus delta, this should have been, I don't even know how to, so there should be a divided by n over here, where you usually got a factor of 1/2 in the binary case. Now you lose it and you get 1 minus 1 over q. So they are no longer matching Hamming at this stage. So in the q-ary case, there's this other surprise, so which sort of motivates my question. If we think the BCH codes are somehow elementary and nice, well, why aren't they working for the ternary case? Why aren't they working for mods, field of 6, for the alphabet of 6 elements, and so on? So we have all sorts of mysteries surrounding them. So which is what I would say is probably a good way to articulate that question. How do we come up with something simple? Well, try to do it in other cases. So I haven't articulated this question clearly here, but feel free to ask me about it later. So going back to the q-ary case, I think this is really the burning question. You have a rate which looks like 1 minus delta minus some function of the alphabet size. What's the fastest decaying function? And give us a natural explanation for why you should even get f of q, which is order of 1 over square root of q. I mean, we can sort of see the algebraic geometry codes achieve it. Somebody states it to me, and I believe it, but I cannot see any natural explanation for why that quantity should be growing as 1 over square root of q. I mean, is this related to anything else that we know anywhere else? There have been no explanations at all for this quantity. Okay.
So where does it come up in the algebraic geometry of this function?
Sorry?
This function comes out of some mathematical result.
Yes. Sorry.
So what is
it comes out of the fact that the genus of an algebraic curve in something the number of rational points divided by its genus grows roughly as square root of q. But that is a very algebraic statement. Yeah.
Is it something that cannot be improved in that context?
It cannot be. Yes, in the context of algebraic geometry codes, you cannot improve that square root of q. But it's not clear how powerful that statement is. Because we don't even know enough about that context to say, well, now we'll play a different game with respect to algebraic geometry objects. Right. It's
So I have a question. Why it seems slightly unnatural to me to look at growing alphabet size, because I always think of Q as prime power and encode the new letters by old letters. So why is it natural to look at Q going to infinity?
So in what sense would you? So you don't want to know the rate or the dependence on Q or no?
I think in applications you think of Q would be a power of Q or power of a prime, and then wouldn't be natural to just...
Sure. Okay. Give me. It doesn't have to be the limit as Q tends to infinity. Give me a limb soup kind of a behavior. I mean, as long as if you can find me infinitely many Qs for which a certain bound holds, I'd be very happy with it. So it's not as if I want it to hold for every Q. I really would like it to hold for infinitely many Qs. Does that answer the question, or?
The answer is that the noise behaves, even if it's a power of 2 and you can encode each letter by 10 digits, still the noise, now when you look at the noise, it's a different noise.
Well, in the real world, do you ever encode something with a number of, I mean...
No, actually, no, it's very true. I mean,
and the whole package will get...
Right, and so typical, by the way, I mean, this is something that I also was forced to learn, but typical encoding of information on your disks is a Reed-Solomon code over an alphabet of size 256. It's not a byte, it's... okay, all right. So, but in general, apart from the engineering implications, I think there's also a practical implication, which is that to construct a good code over a binary alphabet, what you do is you create a good code mapping over, say, 256 as your alphabet, and then you create a small nice code which encodes 256 elements, 2 to the 8 into 2 to the 16 bits. And if you can do a good job with respect to the second part, and you could probably do a brute force search to find it, then the first part becomes a major challenge, and you would like to know how well you do there also. So there is a good game to be played in that size. Okay, so we move to the second part of the talk. There's correcting random errors and correcting worst case errors. There's not too much technically going on in this part, so I think we'll be okay. And I just want to give you a few words about what's going on. So firstly, let's just recall Shannon's result. So I'll talk about the sigma symmetric channel. It has a single parameter p, which defines it, which says, well, any symbol sigma in the alphabet, little sigma in this big alphabet, is transmitted as such with probability 1 minus p, and then you transmit a random other symbol with probability p divided by q minus 1. Okay, that's with an alphabet of size q. And in this case, what did Shannon say? He gave a very nice coding theorem which said, well, you can transmit essentially very effectively at rate 1 minus the entropy of p minus epsilon. And the entropy has been sort of, this is why I sort of perverted the notation so that it doesn't matter. This is the familiar result to most people if q is equal to 2, and if not, then it scales the right way. And in particular, this is a formal version of the theorem. You pick when you have when you fix your rate to be something like this, then for infinitely many n or every sufficiently large n, there exist encoding functions, decoding functions, which map Rn bits to n bits, such that after you take a message, you encode it, then you send it through the channel, then you decode it, you get back your message with probability, which is essentially all but exponentially small in n. Okay, so that's the formal statement, but that's the informal statement. You can transmit at rate 1 minus the entropy of q minus epsilon. And there's also a converse, which is you cannot transmit at rate which is the same quantity plus epsilon. So this theory seems to be ultimately resolved, right? So there's no mysteries left over here. And unfortunately, all of this turns out to be non-constructive. So Shannon's encoding algorithm is you pick a encoding function at random. And the decoding algorithm is you do brute force search relative to this encoding algorithm. So we would like constructive versions, and so what's the story with respect to that? So we should be asking the question, can you make these encoding functions and the decoding functions polynomial time? And the answer is yes, and it's not very recent either. So in 1966, Forney gave already a polynomial time computable encoding and decoding pair. So this is quite interesting because the notion of polynomial time was just emerging at that time, and this is not the first result encoding theory which talks about a polynomial time algorithm. There was a non-trivial polynomial time decoding algorithm for BCH and Reed-Solomon codes like 6 years before that, and then Forney used it as part of his literature. There was also work by Gallagher in between, which was trying to do better, and so on. So even though this is an era when algorithmic complexity was not fully sort of abstracted yet, people had been working on some very non-trivial and very efficient algorithmic questions, and they were finding some very efficient solutions. But it turned out that, well, for a while, Forney's algorithm was considered wonderful, but now of late people have been saying, well, this is okay, but it's not good enough. Wasn't a clear articulation of the question as to why this was going on. So I'm going to rewrite history slightly and then tell you about some more recent results. So in 1994, Spielman, and then using his work, Barg and Zimmer in about 97, came up with linear time encodable and decodable functions. So in n bits you want to encode or decode in time order of n, you'll do everything. And still, this was not satisfactory. Okay, so and you're going to, all of these results are talking about at the Shannon limit. Okay, you're going to converge to the Shannon limit, and still it was not. And then came this result, of course. Since I'm saying I'm revisiting history, there's some sort of anachronism here, but in 92, Beru et al. Came up with this result, which said, well, here is a new family of codes called the turbo codes, and here is an algorithm to apply to their belief propagation. And there were no theorems, but this was very satisfactory. So it's up to us theoreticians to figure out what exactly is satisfaction over here. Okay. So finally, I think Luby et al. In this really wonderful work, or series of works, articulated the question of what exactly are we looking for? What are we trying to chase down? So let's look at the practical interest. So practically, they have very concrete settings of parameters. They say, well, I have 10,000 bits I want to, or I want to transmit 10,000 bit packages at a time. I have an alphabet of size 2. My error probability per bit that I transmit is 0.1. And I'd like to make sure that the entire stream is sort of decoded correctly with probability all but 10 to the minus 6. What's the largest number of message bits I can put in here? So when it comes to this concrete kind of complexity questions, Forney's results were not satisfactory, while Shannon's was considered quite satisfactory. Okay, so if you took Shannon's theorem and applied it in this setting and so on, those numbers were okay, Forney's were not okay. So what's not okay about this? Turns out that in Forney's algorithm, what he does roughly at some stage or the other is he says, well, if I'm working at rate 1 minus entropy of p minus epsilon, then I'm going to have 2 to the 1 over epsilon squared in the running time of my decoding algorithm at some point or the other. And so let's say we are trying to use a channel whose capacity is some number. We want to use it at a rate which is 90% of the capacity. It's a modest ambition. Okay, it's not 100% yet. The decoding time is going to be at least 2 to the 100. And that's independent of the length of the channel. Now, there'll be other factors based on the length. It's this aspect that people don't like, and this aspect which probably needs to be addressed. So the right question, and once again I want to sort of stress that this is what how Luby et al. Phrased the question, is that we would like to have an algorithm whose decoding time is n times a polynomial in the 1 over epsilon, where the epsilon measures the distance between the rate and the capacity. So R, if R equals 1 minus entropy of P minus epsilon, then we'd like an algorithm whose complexity is polynomial in 1 over epsilon. Even if you could do polynomial in n and 1 over epsilon, I don't think the questions change so much. I think the question remains equally interesting. Even if you get a slightly weaker result, this would be quite interesting. And the current state of the art is the following. Luby et al. Proposed the study of codes based on irregular graphs. These are called irregular low-density parity check codes. Since I won't be able to talk much about them, I have a few slides on them, but I won't describe that much to you. So basically, so there were a couple of slides, but I'm omitting them. But they're proposing this study based on irregular graphs. Unfortunately, they don't have any theorems approaching capacity for the erroneous channels. They have a few theorems which are sort of, some distance away from capacity. They have a very strong analysis for a very simple case of errors or simple case of corruption of information. This is the case where a symbol does not get flipped from a 0 to a 1 or vice versa, but it's simply erased. Okay, so somebody goes and neatly erases in all the places where you have symbols, and you do this thing. And in these cases, I mean, they get very strong analysis. Their decoding time is n times logarithmic in 1 over epsilon, while I think if we had used previous techniques, it would have been n times some polynomial in 1 over epsilon or some such thing. So it is a simpler case, but it's been analyzed very nicely, and it really led to some very nice ideas. They do have proposals for errors. They gave an algorithm, and they gave a heuristic analysis which was sort of made rigorous by Richardson and Urbanke, but none of these are converging to the Shannon limit. They're very close. They're close enough that for concrete settings of the parameters you would be very happy with it. So you say their epsilon that they can achieve is 0.0001. Unfortunately, when you say that I can converge up to epsilon equal to 0.0001, you do not converge. This is not a mathematical result. This is just an engineering result. And they have some wonderful results in this theme, and it's somehow merging both the practical challenges and the... So what's still open in this domain is the right question. Can you get decoding whose time is n times polynomial in 1 over epsilon? I think this is probably one of the biggest open questions in this arena. This is probably what is motivating much of the search for these near Shannon limit codes that's going on in the literature, and it would be very nice to have a result which actually is accompanied with theorems in this setting. So moving on to the last part, I'll talk a little bit about how to correct or what is the questions related to correcting adversarial errors. And so these are cases where so far the Shannon setting was every bit was being flipped at random. And when bits are being flipped at random, there's a sort of a very simple idea which was used in Forney's thing, saying how would I sort of control the errors. And what you do is you just take your bit sequences and divide them into moderately small blocks of size about log n. And over here you have error correcting codes within each block. Well, it doesn't matter what your decoding complexity is as long as it's exponential. You can correct any errors that happen inside the block in polynomial in n amount of time. And that is very useful in the random error setting where the errors are all distributed nicely evenly. In the adversarial error setting, this does not happen. You cannot figure out a breakdown of the message first and then wait for the adversary to get their hands on this encoding. And why do we care about this? Well, there is, I think, practical motivation. I think as notions of communication and storage get more and more complex, I mean, we cannot afford to model error as an oblivious process which is sort of independent of how you encode, how you decode, what messages you're sending. I mean, these are all too simplistic. I think it's much more reasonable to come up with sort of broad, all-encompassing models where you're not trying to over-determine the system. And that's roughly what adversarial errors are trying to do. It says, I don't know how these errors happen, but given that they've happened, this is how we'll try to correct them. So these are more, and
When we say it's really completely unrealistic, the independent error model is I mean, no particular person would say that this is, errors often come in bursts, in reality. So.
Okay, so it's a good point. So Nati points out that the independent error model is completely theoretical, which is true. It wasn't used in the practice either. In the practice, typically they come up with a bursty model or with a Markovian model, or they come up with blended models, 3 bursts and 20 independent errors. Okay, so in general, these codes and the algorithms have been getting so fine-tuned to the model now. I mean, you can see that the model is getting sensitive, and your algorithms are getting sensitive to the model. And now suppose a new cell phone player enters the market tomorrow and sort of starts creating new turbulence in the airwaves. Does that mean we're going to go and reset all our cell phone decoding algorithms? This seems like a rather over parameterized, over carefully analyzed system. So I think we should be moving over to a scenario where we sort of abstract a very gross limit on model on the error. Lots of things can fit within it, and within that we don't care. So what would we ideally like? Well, errors are worst case. Unfortunately, what happens is that when you have errors which are worst case, we have a gap between the worst case and the random setting. So for example, in the simple case, we are transmitting bits. Shannon says we can deal with error which is arbitrarily close to 50%. In the Hamming model, where the errors are worst case, the best distance you can achieve in an error correcting code is relative distance is 50%. So 50% of the bits will differ. And under the unique decoding model, where we said, well, we're going to correct half the distance, you can correct 25% errors. So this is a pretty serious gap. And if you go up to a practitioner and you say, well, okay, as long as you're willing to sort of live with only 25% error, here's a better algorithm which will work with worst case error, this does not fly. Okay, so unfortunately, this is too large a gap to go from the overdetermined model to the underdetermined one. So we need new approaches to bridge the gap. And what I'm going to tell you about is some of the work that I've been doing, and also Venkat here, on what we call list decoding. And the reason this becomes relevant is that the main reason for the gap between Shannon and Hamming is this unique decoding feature. Say, well, every time there is an error, you must you must uniquely recover the message. So list decoding says, well, we'll have a relaxed notion of recovery from errors, and the decoder would, rather than producing a single message saying this is what was sent, will produce a small list saying one of these was sent. We're going to throw, for the time being, I will discuss this later in a few slides, but for the time being, we'll just say, well, we'll just throw it in the user's lap to figure out what to do with this list. Okay? The user is somehow going to have to figure out what to do with it. So in this model, we'll come up with a new definition. We'll take a code which is trying to deal with fraction p of errors, and we'll say that it list decodes with parameter L, with lists of size L, if no matter what you transmit, and a fraction of p errors happen, no matter where, there is an algorithm whose running time we don't care about again, at least now. You can come up with a list of size at most L which will be guaranteed to include the transmitted message. Okay? Does this make sense? You can formalize it in other ways, but just for now we'll just define it functionally. This is what it's supposed to do. It's too late. I seem to have 2 copies of that slide, and the second one was, doing the right animation. But anyway, so the wonderful news in this setting is a fairly old result of Zyablov and Plinsker, Blinowski, etc. contributed to this thing. It was mid to late 80s, where they say that there exist codes whose rate is 1 minus entropy of p minus epsilon, which are p order of 1 list decodable. So what does it mean? It means that if you have fraction p of errors and they are adversarial, then you can produce a list of size, constant depends on epsilon, 1 over epsilon squared or something, and they are decodable to within rate 1 and these codes have rate 1 minus entropy of p minus epsilon. What's the difference with respect to Shannon? Well, none quantitatively, and qualitatively there are 2 differences. Shannon assumes random errors, we are not. But these results assume that you're outputting a list. Okay, so wouldn't it be wonderful to have algorithmic results to match this? Unfortunately, we don't. At the state we are in fairly primitive stages of this analysis. constructively what we can show is that there exist binary codes whose rate is roughly 1 over epsilon to some constant that can correct 1/2 minus epsilon adversarial errors using lists of constant size. So what does it mean relative to this? It says if the code has positive rate, then you transmit at positive rate. If a channel has positive capacity, you transmit at positive rate. But these two are not matching each other, unfortunately. So this is some constant C. So what is C? Well, good question. C is right now we're getting binary codes of rate 1 over epsilon to the 4th, etc. I think there's an upcoming result which should imply that you should be able to get C down to about 3. 1 over, oh, I'm sorry, right, yeah, okay, these should be epsilon to the C. I needed you. I owe you one. See, these talks are so good. They're self-correcting. All right, so minus C equal to 4 and minus C equal to 3, epsilon, codes of rate epsilon cubed or something. Ideally, what should be the right number if we are trying to get, even at this error rate, what should the right number be? It should be epsilon squared. That would be the Gilbert-Varshamov, that would be the Shannon capacity 1 minus entropy of P, where P is 1/2 minus epsilon, is about epsilon squared. We are far away from that criterion, so this would be the major challenge in this setting. So the major challenge is, of course, to construct these kinds of codes which achieve the thing with polynomial time list decoding. And if the running time is polynomial in 1 over epsilon also, I mean, let's throw that in as a bonus since we're wishing for a lot, let's wish for a little bit more, then this would be the complete solution to all the decoding problems that we've encountered in this talk. Okay, so that would dominate the problems that we've set up in the random error setting as well.
So I know the list sizes are exponential?
I don't know how to do this. Sorry, what's the question?
Right now the list sizes are exponential and
no, the list sizes are okay, are polynomial. What we would like is we don't know how to solve this problem. When I say polynomial time, I would be thrilled if you could do this with polynomial time in n with any dependence on epsilon. But if you could do it with polynomial time in n and polynomial in 1 over epsilon, then you've solved all the coding theory algorithmic problems that we've described in this talk. Okay, and here's just a few words about what can we do with the list, just because I don't want to throw it up with the user's lap. One reason why the list is considered okay is that if you were in a probabilistic setting of errors, though you hadn't modeled the situation very carefully, well, in such situations you can easily prove by probabilistic methods, there's no algorithmic question remaining, that for typical error patterns the list has one element. So the algorithm might report a larger list, but only if the errors were adversarial. But if the errors are actually probabilistic, it would still work and it would produce a list of size 1, so you're done. Some other interesting answers that have been ways of formulating it. Venkat asked this question about, what if you had some side channel going on between the sender and the receiver, which is very expensive to use, but is also something that you can use. And he showed that you can actually send about log n bits to disambiguate the list. So you have a polynomial size list, log n bits should suffice, and indeed they do. And in fact, he showed that you can actually send these log n bits, before any of the transmission happened, as long as the adversary is not aware of what's going on. So in an alternate way of describing a similar result, Langberg says that, well, if the sender and the receiver share some log n bits which are not known to the adversarial error, to the error channel, then it's very unlikely that it can create an error which cannot be disambiguated. And finally, there are some new studies going on. Actually, not so new. Lipton started this work in '94, but then they're still writing the journal version. And he introduced this notion of an erroneous channel, which is a computationally bounded error channel, which is a beautiful model, which says, what would you like from the model of an error? Well, a gross upper bound on the number of errors is necessary, or else 100% errors happen. What can you do? So under this assumption that there is that you have a gross assumption on the error, what else would you like to assume about the adversary? Well, ideally nothing, but the worst case adversary is creating some problems and we don't know how to disambiguate uniquely. Well, maybe if we just make the adversary computationally limited, which is quite a natural thing. I mean, everything we've been considering, I mean, if p equals np, or if the adversary can actually invert all one-way functions, then they can do much more damage, so we don't have to worry about them introducing a few errors in our communication. So in assuming that the adversary is somewhat computationally bounded and it's not doing all kinds of unreasonable things, see, it's just our fear of, we don't want to model the system too carefully, but saying that it's only doing polynomial time computations is a very reasonable model. In this case, we can actually extend many of the list decoding results so that you come up with a unique answer, and this unique answer sort of needs some basic infrastructural assumptions, but other than that, I think it's a fairly reasonable solution to these cases. So all of these sort of further enhance the list decoding question. I think it's a very important question which we would love to see some progress on. So finally, so just to stop, I mean, there are many mysteries in the combinatorial setting. The combinatorial setting is mostly a collection of very intriguing questions for which we don't know what the answer is, but I'm not 100% convinced that needing the finding the answers is going to radically alter anything. On the other hand, in the algorithmic setting, I think the questions are really, really deeply sought after, and there's a lot of ongoing work, and it would be very nice to see some new ideas there. Okay, let's stop.
Nada, you must have.
He has answers.
What's the best known decoding algorithm for the algebraic geometry codes?
What's the best known decoding algorithm for the algebraic geometry codes? Save me on this one. So in terms of how many errors it can correct, or the running time bounds, and
well, either one. I was thinking about the running time, but
the running time. I think the state, at least cubic. Yeah. So I think by now there are. So one of the things about the algebraic geometry codes is that the first results were purely existential. It took a while for us to realize that you could construct the associated encoding matrix, for example, in polynomial time, and the initial polynomials were n to the 30 and so on and so forth. By now, those constructing the encoding algorithm, we've sort of reduced it to a complexity of n squared or n cubed, and similarly for the decoding algorithm also the complexities are very similar. But these are cases where just identifying the right arena to work with, identifying a polynomial number of bits which would specify the encoding and decoding algorithm takes us all the time, and then actually the algorithms for encoding and decoding can be pretty much faster. I don't think we have, it takes as much time as reading the information, so it's at least n squared, it's at most n cubed, but that's the setting where these.
And who's the decoding algorithm too?
So I would suspect all of these results should somehow or the other follow from Schum's thesis. Is that right? Do you know the name by any chance? Kenneth Schum, S-H-U-M, and it's a thesis from somewhere in Southern California. I forget. Yes, so there's a question in the back, sorry.
In machine learning, belief propagation is sometimes used to do inference for hidden variables, and then belief propagation gives you marginals over hidden variables. And there has been some work on trying to, instead of having just marginals, hidden variables, having multiple marginals, so that when you put these multiple marginals correspond to different nodes of the distribution. Could something like that be used for your list decoding, or has it been used for list decoding?
So, okay, so the question was whether some of the techniques used in belief propagation, in particular in the machine learning, coming from the machine learning community, have been used in list decoding. So in list decoding so far, no, we're not that close to capacity to be worried about such small changes in the marginals. In the random error setting, there are people who are applying some sophisticated techniques, some concentration results that I know about to make some of these Luby et al. Results, for example, to make them rigorous. Richardson and Urbanke had to use some of the state-of-the-art techniques. I don't know what the origin of these techniques is and what exactly goes into those results. But if you're interested in seeing where the belief propagation results are being applied, that would be roughly in the random error setting, and it would be trying to get near capacity with low complexity. But I haven't seen any theorems derived from that either. It's typically at the state where we are saying we can, we seem to be able to do better than otherwise, but neither of these can be analyzed. Yeah.
So for the list decoding settings, are we at the stage yet where the results that we have are satisfactory?
Oh no, definitely not. I mean, we would be very satisfied with the list decoding results if they beat the random error results, right? So we definitely want to.
So whatever we can do analytically, can we do it fast enough for it to be?
Okay. So in terms of algorithmic complexity, how good are these list decoding results? Venkat has been working on some of these things with Piotr Indyk, and I think their results are pretty competitive. I don't think they're matching every setting of parameters, but I think there's a large variety of parameters where whatever we could do in polynomial time, they can do in linear time, and so on. So I think we are in pretty good shape. But this notion of polynomial dependence on 1 over epsilon, well, we're not even close to that. But that will be the next stage of the challenge. Right now, we are only measuring running time as a function of the input length n, and then they are very good. Yeah.
Quick question: this decoding or this coding stuff, the main interest is coding for channels with memory. I mean, it's applicable.
It's applicable to coding for channels with memory, but in general, it's applicable for coding with channels with any kind of adversarial information. In particular, these may be channels which may know how you encode. So they've seen your encodings pass by for many, many times. They've seen things happening, and now some sort of. It
seems to me like there's some fear addressing evaluation of performance for such channels. I mean, you come up with a coding scheme, but when it comes to evaluating these channels, there's so many assumptions of making the send infinite interleaving or whatever. And it's just like there's very limited literature on error control codings for channels of memory.
Right. So my sense is, I agree with you. I think in general, there's a lot of literature on how to analyze the channel carefully and do well on those. I think we should have been investing in the other basket also, which says how do I ignore the channel and draw very rough qualitative bounds out of it, or one parameter, and try to build coding schemes for those. And it seems, I think one of the big things was this did not look feasible maybe 10 years ago, and maybe now it looks feasible. So now that it looks feasible, we should examine it further.
Yeah. But there's some surprising, unusual applications of all these theories, something that goes beyond what we usually think about communications.
There have been quite a few. Unfortunately, there are. So there's quite a few. So many of these questions were actually, to be honest, not motivated by communications, but rather when we were trying to examine various complexity theoretic assumptions, various in computational complexity, saying, well, if we can solve this. So here's a quick example. I take a permanent of a matrix. It's a well-defined mathematical computation, sort of like the determinant of a matrix. There's a related quantity called the permanent. If you want to compute the permanent, it's very hard to compute. There was a formal result which said, well, if you try to compute it on a random matrix, it's as hard as on the worst one. And trying to figure out how hard this could be led to some of the questions that were addressed by the list decoding answers.